China is accelerating its push toward its first crewed moon landing before 2030, unveiling an ambitious program that blends cutting-edge engineering with a step-by-step, risk-managed approach designed to make the mission both achievable and sustainable, with its centerpiece being the Laney lunar lander. A single-stage craft capable of handling both descent to the moon's surface and ascent back to lunar orbit in one integrated vehicle, eliminating the need for separate modules and thereby simplifying operations while increasing structural efficiency. This design relies on 4 powerful main thrusters arranged symmetrically around the crew cabin for balanced thrust, complemented by an outer ring of smaller reaction control jets to ensure fine maneuvering capability and crucial redundancy, allowing the mission to continue even if one engine fails during a critical phase. To prepare it for the moon's unique environment, engineers have tested Laney using a massive tower and cable suspension rig that offsets 85% of the craft's weight to simulate the moon's lower gravity while eliminating the effects of wind and atmospheric turbulence. A system refined from earlier Mars mission testing that proved successful with the Tianwen-1 lander. The mission architecture involves pairing Laney with the Mango crew transport spacecraft, which will serve as the main link between Earth and lunar orbit, with the 2 spacecraft launching separately aboard Long March 10A heavy lift rockets, each a triple-core booster with 7 liquid-fueled engines per core, delivering immense thrust and payload capacity comparable to SpaceX's Falcon Heavy, before meeting and docking in lunar orbit for the crew transfer. This twin-launch strategy not only spreads the enormous mass requirements across 2 missions, but also allows for more robust hardware, extended surface stays, and potentially larger crews. Backed by supporting technologies such as the Wangu Lunar EVA suit, designed for greater mobility and extended use on the moon's surface, and the Tenno rover, a lightweight electric vehicle capable of ferrying astronauts and equipment across several kilometers of rugged terrain, greatly expanding the exploration range. While China's program is built on state-backed resources and a long-term vision, a different but equally determined effort is underway in the United States through Rocket Lab, a private aerospace company that has built its reputation on the smaller, highly reliable Electron rocket, with 65 successes out of 69 launches, and is now stepping into the heavy lift arena with Neutron, its first large reusable rocket, representing a major technological leap aimed at competing in both commercial and government launch markets. Neutron's development centers around the newly tested Archimedes engine, which has already completed a full-power hot fire in a flight-ready configuration rather than an experimental prototype, signaling the company's confidence in its design maturity. And the rocket itself will feature a highly innovative reusable clamshell fairing that opens like a set of doors to deploy payloads before closing again, remaining attached for reuse, thereby eliminating the need for separate fairing recovery operations. The booster is designed for full reusability with the potential for land-based propulsive landings or recovery on floating platforms, though the debut flight from Wallops Island, Virginia will aim for a controlled Atlantic splashdown to gather performance data before moving on to precision landings, with Wallops chosen strategically to diversify U.S. launch capability and reduce dependency on Cape Canaveral, enhancing resilience in case of local disruptions. Rocket Lab's ambitions extend beyond orbital launches into national security, positioning itself as a key contractor for the $175 billion Golden Dome missile defense program, which aims to integrate space-based detection and interception systems for ballistic threats, a move bolstered by the $275 million acquisition of Geost, a company specializing in missile tracking, space domain awareness, and orbital surveillance technologies, effectively giving Rocket Lab the capability to provide not just the launch services but the satellites and sensors themselves, creating a vertically integrated space defense portfolio. In addition, Rocket Lab is reconfiguring its proven Electron platform into HASTE, the Hypersonic Accelerator Suborbital Test Electron, designed to carry a 700 kilograms payload on suborbital trajectories for military and rapid delivery applications, with its exact missions kept classified but likely to include hypersonic weapon tests sensor validation, and potentially ultra-fast cargo deployment to any point on Earth, further diversifying Rocket Lab's revenue streams while enhancing its role in defense. Together, China's state-led, methodical lunar program and Rocket Lab's aggressive expansion into heavy lift, reusability, and defense applications embody the rapidly evolving nature of the 21st century space race, one that is no longer defined by a single bilateral rivalry, but instead by a dynamic and competitive ecosystem involving nations, private companies, and hybrid partnerships, all driven by both exploration goals and strategic imperatives. In this new era, the moon is more than a scientific destination. It is a proving ground for deep space capabilities, a staging point for Mars and beyond, and a potential site for resources such as water ice that could fuel future space economies. And both China and Rocket Lab are acutely aware that leadership in this domain will be determined not only by who arrives first, but by who can operate reliably, sustainably, and repeatedly in the harsh environment of space, setting the stage for a decade of unprecedented technological leaps, geopolitical competition, and human achievement as the boundaries of exploration continue to expand. China's advancing lunar program and Rocket Lab's aggressive market expansion are only two threads in a far larger tapestry of global space activity, as Europe, India, Japan, and emerging spacefaring nations bring their own ambitions to the table. The European Space Agency is advancing the Lunar Gateway Partnership, contributing modules and logistics that could serve both NASA's Artemis and future international missions, while India, fresh from the Chandrayaan-3 success, is developing its own next-generation crewed spacecraft, Gaganyaan, as well as exploring lunar resource extraction concepts. Japan, through JAXA, is pursuing precision lunar landings with SLIM and collaborating on advanced robotics for surface exploration, a capability that could dovetail with crewed missions in the 2030s. Even smaller nations and private firms are entering the arena via rideshare programs and microsatellite constellations, leveraging lower launch costs to participate in research, technology demonstration, and even commercial services on and around the moon. What's emerging is a space economy that blends exploration with commerce, science with national strategy, and competition with cooperation. On the commercial side, lunar mining concepts, particularly the extraction of water ice for life support and propellant production, are attracting investment from both state-backed and venture-funded entities, with pilot projects exploring in-situ resource utilization, ISRU technologies. On the defense front, the militarization of cislunar space is increasingly under discussion as governments recognize that future lunar infrastructure will require both surveillance and protection from potential adversaries. Meanwhile, reusability, once considered a risky gamble, is becoming the baseline expectation for competitive launch providers, driving costs down and enabling higher launch frequency. As space agencies and private firms move towards sustained lunar operations, the challenge will not just be technological, but logistical, maintaining supply chains, ensuring crew safety, building redundant systems, and managing the legal frameworks for resource rights and orbital traffic. In this landscape, the true winners will be those who can integrate capability, adaptability, and resilience, turning the moon from a distant target into an operational hub for humanity's next great leap outward. China's advancing lunar program is centered on the Long March 10th heavy lift rocket, capable of placing 70 tons into low Earth orbit and 27 tons into translunar injection. With its dual launch profile, sending the Mengzhou cruise ship and Lanyue lander separately to lunar orbit, where Lanyue, a 26,000 kilograms single-stage craft with four 7,500 main engines, numerous attitude control thrusters, and autonomous hazard avoidance systems, will handle both descent and ascent. The lighter Long March 10A variant, standing 67 meters tall, will debut as early as 2026 with a 14,200 kilograms LEO payload in reusable mode, serving as a stepping stone toward the full mission. Meanwhile, Rocket Lab's Neutron, a 43-meter-tall, 7-meter diameter medium-lift reusable rocket with a 5-meter captive fairing, can deliver 13,000 kilograms to LEO, 15,000 kilograms expendable, and 2,000 kg to translunar injection, powered by 9 Archimedes methane/LOX stage combustion engines on the first stage and 1 vacuum-optimized Archimedes on the second, with the engine having already completed a full-duration hot-fire test in flight configuration as of August 2025. Neutron's composite structure saves up to 40% in mass over metal rockets, and its Hungry Hippo integrated fairing eliminates separate recovery operations by staying attached, opening to release the payload, and closing again before stage recovery. Its development milestones include completed launch pad construction, stage build, static fire, and wet dress. Rehearsals in Q3 2025, with the first test flight expected later in 2025 and a confirmed multi-launch customer contract for 2026. Together, China's phased heavy lift, lander, and crew transfer plan and Rocket Lab's innovative, reusable medium lift solution mark a convergence of state-led lunar ambition and private sector launch innovation, signaling an era where strategic simplicity, engine maturity, and reusability set the competitive standard for both exploration and space infrastructure.